Section 4.5 is about dimension. Let's begin with the theorem that says, let V be a vector space that has a basis consisting of a finite number of vectors. V1, V2, V up through Vn be the vectors in one particular basis. Theorem says that then any other basis of V also has the same number n of vectors. This number n is called the dimension of the vector space. Let's look at a simple example of R2. So as we've seen, this has the basis called the standard basis, E1 and E2, where E1 is this vector 1, 0, and E2 is the vector 0, 1. Here I've written them as column vectors. And so the theorem says that any other basis of R2 will have to have exactly two vectors, since the standard basis has two vectors. Okay, so let's just pick two vectors. Well, here's one vector 1, 1, and here's 2, 2, but actually this is not a basis because they're not linearly independent. This one here is just double this one. So this theorem is not saying any two vectors will form a basis. We have to choose the two vectors a bit more carefully. So let's try 1, 1 and 2, 3, and these will form a basis because the determinant of the matrix formed when you throw those column vectors into a bigger matrix, this matrix has non-zero determinant, and therefore we've seen in a previous video that these vectors are linearly independent and therefore will span the vector space, since the vector space we know has dimension 2. Here's a picture illustrating the previous two examples. First, we tried the two vectors 1, 1 and 2, 2. They were pointing in the same direction, whereas if we chose 1, 1 and 2, 3, they're not in the same direction. All right, let's do an example from Anton. It says, find a basis for the solution space of the homogeneous linear system and find the dimension of that space. So first of all, this term homogeneous, when referring to a linear system, just means that the numbers here are all 0. So the solution is to form the augmented matrix and then row reduce. To get a pivot 1, what I've decided to do is add to this row -2 times the first row. So here's -2 times the first row. I'm adding it to the second row, and when I do that, the -6 and the 5 turn into a -1, and so that's down here. So I've replaced this row by adding to it -2 times the first row, and then I'm multiplying this row by -1, and then I get this matrix here. So now I've got this pivot 1. Next, I've interchanged the two rows, so I brought this pivot 1 into this position. Then I'm going to replace row 2 by adding to it -3 times row 1. Here's -3 times row 1. I add it to row 2. I get my 0 here. Then I divide through by -2 to get here. And then I decided to just stay in this row echelon form and not go further and reduce it. So then this equation here turns into x2 plus 1/4 x3 plus x4 equals 0. So that means that x2 is this linear combination, and that x3 and x4 are going to be free variables. And then this top line here turns into this equation here. x1 is this, by moving all this to the other side, and then I know what x2 is in terms of the free variables x3 and x4, and then I finally get that x1 is equal to -1/4 x3. Here I've added now the code to do this in Sage. A is the matrix with coefficients in QQ. It's a 2 by 5 matrix, and I've entered the first row and second row, and then I just find the reduced row echelon form of A, and it gives me this, and this translates to x1 plus 0 x2 plus 1/4 x3 plus 0 x4 equals 0. That's what the first row translates to. And the second row translates to 0 x1 plus 1 x2 plus 1/4 x3 plus x4 equals 0. And so from these, you see that x1 is equal to negative 1/4 x3, and x2 is equal to negative 1/4 x3 minus x4, which are the same things we've found. Okay, we're still trying to find a basis for the solution space. We found now, so far, the solution space. So x1 has to be negative 1/4 x3, x2 is this, x3 and x4 are free variables. Okay, and so then the trick is to factor out the x3 and x4, if you will, and write the solution space as some combination, some matrix, some vector times x3 and some vector times x4. So remember, x3 and x4 are the free variables, and so then these two column vectors here will form the basis for the solution space, because any linear combination of them, namely this linear combination given by x3 and x4 as the coefficients, will give rise to a solution. And so this, because there's two vectors here, the dimension is 2, the dimension of the solution space is 2. Here's another example from Anton. It says, find a basis for the given subspace of R3 and state its dimension. So here's the subspace. It's just given by a single equation, and we do the same procedure. We form the matrix, the augmented matrix. This time it just has one row. We get it into, this is actually reduced row echelon form by dividing through by 3 or multiplying by 1/3. And so we get this, and so this tells us that x minus 2/3 y plus 5/3 z is equal to 0, and that therefore x is equal to this combination here. Y and z then are the free variables. They can be anything, and then as long as x is this, given by this equation, then you'll have a solution. So our solution xyz is like so, and then factor out the y and the z since they're the free variables, and we get the column vectors shown here. And so therefore a basis is given by these two vectors, and these two vectors will always be linearly independent. You can see that by they have this 1, 0 and 0, 1, sort of similar to the standard basis vectors in there, and so they'll be linearly independent, and therefore the dimension of the vector space they span is 2. Moving on to part C, the question again is find the basis or a basis for the subspace given. In this case, the subspace is the line given like so. So let's write it as a column vector. X is equal to 2t, y is equal to negative t, and so on. And so our free variable is t. Let's factor that out, and so we get this. And so therefore, this column vector 2, negative 1, 4 is a basis, and therefore the dimension is 1, which is no surprise since it's a line. Then part D says find a basis and dimension of all the vectors of the form ABC, where B is equal to A plus C. Okay, so writing this ABC as a column vector, we are given that B is equal to A plus C. So A and C are our free variables. Let's factor them out. And then we see that we have these two vectors here as a basis. And so therefore the dimension is 2. Okay, problem 12 says find a standard basis vector. So that's either E1, E2, or E3 of R3 that can be added to the set V1, V2, where V1 and V2 are these given vectors to produce a basis for R3. So to check if something is a basis, well, one way to do that is throw these vectors into a matrix, into a 3 by 3 matrix. Well, so this first vector here, I've written it as a column vector -1, 2, and 3. The second vector 1, -2, 2, written as a column vector here. And then we have to find what goes here, either E1, E2, or E3. Maybe there could be multiple possible correct answers, so that the determinant of this matrix is non-zero. That's a condition for which the 3 vectors would form a basis. Okay, so expanding this determinant by expansion by minors along this third column, we get that this is the determinant is equal to A times the determinant of this 2 by 2 matrix. 2 times -2 is -4 minus a -6, so it turns out to be +6. Then we have to switch to subtracting B times the determinant of the 2 by 2 matrix you get when you cancel out this row, cancel out this row. So it's the -1, 1, 3, -2 matrix. So -1 times -2 is 2. That's how I got this 2. And then you subtract off the other diagonal 1 and 3, 1 times 3. So you get this. And then finally for C, you do plus C times the determinant of the 2 by 2 matrix here. So -1 times -2 is +2, and subtract off the off-diagonal terms, which is multiplied at 2 as well. Okay, and so then when we simplify this, we get 2A plus B is the determinant of this matrix, and we want to find A and B such that this sum here, 2A plus B, is non-zero, and where A, B, and C come from one of these standard basis vectors. And it turns out that E1 and E2 will work, because when you have E1 as A, B, C, so A is 1, B is 0, C is 0, 2A plus B turns out to be 2, which is non-zero. Similarly for E2, you get a non-zero entry. Now if you chose E3, that would not work, because that would give this thing being a 0. So the answers are, well, E1 or E2 or both.